Well, good afternoon. As our professor said, we are the FSAE team suspension design for the 2017 year, and my name is Yussimil. Libera.
Benitez. Mateo, Restrepo.
Qureshi.
So our motivation is to compete on the side of automotive engineers. We're going to compete against over 100 teams, and we're going to have several dynamics tests, which we definitely hope to pass. And the problem statement was to create a fully functional suspension system for a small type of race car. So a little bit about our literature survey. Our suspension is composed of the tires, the wheels, the hubs, the uprights, the control arms, steering linkages, spring, dampers, the geometry, the kinematic analysis, the vehicle dynamics, and the selection and use of the material. So all that involves our senior design project. The upright is the part that connects pretty much the chassis of the car to the wheel, and a lot of the geometry and the dynamic performance of the car lies on how the upright is designed. So the upright is going to have several crucial factors, which is caster, camber, steering axis inclination, etc., which is definitely going to affect how our car will perform. So it's a lot of really important. Also, the integrated tripod. This is something that was new for our team. It was never done before, which is a hub and it's an integrated tripod, and we reduce a lot of the weight doing it this way, and we also increase the power transmission. Here you see a picture of the steering arm all the way to the right, and or rotor that were designed for friction, like for the release of heat. And here you see our A-arms, and as well as our front and rear belt racks. So a little bit about how we started. As I said, we started doing the geometry analysis. So where do we want our suspension points to be? What is our primary purpose in this way, like in the dynamic testing that we were going to have, and we decided where a roll center was going to be, and therefore that's kind of how we started. These are some sample calculations, so it's how we calculated the brake forces and the lateral weight transfer, which later we used to not only include these values into our simulation, but as well to choose the proper bearings to withstand the loads, and as well as to choose a bigger caliper area. This is the steering increment analysis that was done in order to see where we wanted our steering arm to be at and how this was going to affect our steering and, again, the performance of our car.
So with all of these parts that we have to design and manufacture, we have to follow certain standards. In this case, we have to follow closely all the FSAE rules since we'll be competing for them. So we have to just mainly meet the main criteria for them was that no point of the car except for the wheel should touch at any given moment. So there had to be a certain ride height. As far as the SAE, it was mostly done for safety, so our bolts and all of the torque spec we chose were due to SAE rules. And then for ASME and STM was for the material selection, that's why we chose aluminum and some steel. So for project objectives is that we are going to be racing for, we'll be graded on the suspension aspect, and we hope to achieve 20 out of 25 points in the suspension part, and also overall of 50 points in the entire competition. 15th place. As for assigning global design, what we ended up doing is we tried limiting all the sizes for bolts so we can have ease of assembly. We also tried to ease of manufacturing. So when we were designing the uprights and the hubs, we tried to choose radiuses that required tools to be standard tools instead of purchasing really expensive tools. This kind of limited some of our safety factors, and we could have gotten, we can always get a better safety factor, but the cost would always rise, so we have to do some management with that. We're also providing a dual language catalog, which will explain the assembly process in case any part of the suspension has to be taken off or adjusted. For our constraints, some of our main constraints was time. We had to do all of the design work and all of the planning in all of Senior 1. And some of the build, which was manufacturing, also started during Senior 1, which was last semester. This semester, we continued with the manufacturing and the assembly process. As far as money, since we're an FSAE team, we have to spend or separate our monies into individual groups. So we have a certain amount of budget that we have to try to meet, and therefore choose our parts. For the SAE rules, it also limits us in certain things that we can do. In our case, we just made sure that everything that we built on made a certain so that the car wouldn't touch the ground. So some of our safety factors are a little high just to prevent this. So here we're going to start showing some design alternatives. We're going to just show two of the main design alternatives. We went through a lot of iterations through the upright and the hubs to get some better results. So these are the ones that you'll be showing. So this is one of our first design alternatives. Here you can see each component. So in this case, this is the front upright, this is the hub, and then this is the rear. Some of the key things to notice here is that this one was, they had some failures which prevented us from choosing this design, but from this design we based off our feature, the one that we're proposing. For this hub, there are certain issues. In this case, we needed to find a way to properly attach it. And then for the rear upright, it ended up being heavier than the one the previous year, so we had to modify it. As for design alternative 2, here you'll notice that the shape changed a little bit from the previous design alternative. We noticed that we ended up getting better safety factor of safety along with better stresses. As far as the hub, here you notice that we had to put a thread in order to prevent it from, in order to be able to attach it with the, we were planning to put a knot on it. What happens is that when we priced it, it was very expensive to do this threading, so we had to go through a different route. And as far as the last picture there, which is the rear upright, what we ended up noticing is that at the top it was very thin, and we had some issues with that, which we needed to fix. So this is our proposed design. This is our finalized design. And then in the next slide, you'll be able to see that they're very similar.
We conducted simulations on all the major components of the suspension. Due to the time constraint of this presentation, I'm only going to be covering the front and rear upright and hubs, and the forces that were placed on the components will take into account the forces due to maximum acceleration, hard braking, and short cornering. Over here we can see that the results of the simulation for the front upright. We see that we have a factor of safety of 3.1, and then we see that the maximum stress is occurring where the lower A-arms connect to the front upright. Then next we have the front hub, factor of safety of 4.8. We kept the factor of safety for the hub a bit high, just because we were introducing the integrated tripod hub in the rear, which we'll see in a sec. But we see the maximum stress is occurring on an edge where the rotors will be connecting to the front hub. For the rear upright, we have a factor of safety of 2.14, and maximum stress is occurring on the top portion of the brake caliper mount, and the maximum, it's only going to have that stress when it's maximum braking occurring, really hard braking, which wouldn't usually be occurring. And for the rear hub, we kept it a higher factor of safety because it is the integrated tripod hub, and because it's the first time we were doing it, we wanted to make sure it has even more of a safety factor. And we can see that the maximum stress is again occurring along this edge where the hub is going to be mounted to rotors. Over here, these components we manufactured, and you can see the bell cranks and some shims that we were using in our components. In the middle, we have a tool that we actually made because the tool is being too expensive to buy. We actually manufactured the tool ourselves and we treated it to press fit the bearings. And on the right-hand side, we can see so for the smaller components, as in the upright mounts for the chassis, the AR mounts for the chassis, we went to a water jet company to get them to cut out the parts. For the ARMs, we cut up the tubes, and one of the problems that we were capturing with the construction of the arms was that the tubes were hardened and they were small, so threading that we had to do inside was coming out to be difficult. We still did the threading so we can attach the rod ends to it. And then overall, these are the components, the actual assembled suspension pieces, minus the AR being attached to them. Going on, over here we can see Michael and Yussimil working on making the heat treatment of the press fit tool. And on the right you can see Mateo and I. We're adjusting the A-arms to the specified preset lengths for beginning. And a lot of manufacturing was helped out by the team. We have a great team, so without them, within this time limit, we would not have completed all the construction of the manufacturing. Right here we can see the completed car is assembled. So with the suspension, right now currently, the aero team put the bodies on the car. So right now it's at this point, and with the final adjustments to the car, it can be completely ready to go.
This is our testing run. Transport Force teams went out to the Homestead Speedway, and we were able to use their track successfully, and we thank them for that. We took out the car and we were maneuvering in ways that we will be maneuvering in the competition. At the beginning you see when we get a close-up of our suspension, we're going slow through the turns to make sure everything was complete and in place and nothing bending out of the ordinary. And then as he continues, on the following clips, you'll start seeing the compressions of the spring as we start telling him to start pushing the car a little bit more as the drivers get more comfortable with the car. So following right here, you can see. It is a couple laps, and we switch drivers in between. It's a circuit. And this was to be expected, and we're actually very satisfied with the results we got from the testing. And here we switch off the drivers just as competition requires. All right, so this is our cost analysis. Projected at the beginning, we had a $14,400 inventory, but in actuality, we have constraints, so we had to follow them. So our total ended up being $7,200. This is our Gantt chart. We successfully followed our timeline. Again, due to our team, we appreciate every person that was able to help us. And right now we're still on the testing stage and completing the car as a whole. Our competition is in May, the second week, so we are right there. Divisional responsibilities, we try to separate everything equally as best as we could. Design experience, standard views, we will be using ASME and ASTM throughout through our career. So we expect to see it more often. SAE we had to use again because we're part of SAE, and formula because we are doing the formula. Contemporary issues, the budget, we have the third world countries as well. We had to take into consideration that our budget can't be as high as other formula teams are, so our budget is actually relatively probably one of the lowest throughout the teams. And our impact, global constraints, once again, the budget is the biggest constraint that there is around the world. Lifelong learning, working with others. We have multiple teams and multiple opinions, multiple cultures that we'll be running into. And you have to be very open-minded and be able to accept other people's opinions and look throughout to complete and have a successful career. And then we have learned to be professional and meeting deadlines. We have 3 different people that we have to meet deadlines with. We have the class, we have FSAE, and we also have SAE that we have to meet deadlines with. So we had to be as professional as possible with that. there's always a better way. As we saw, we have a lot of iterations coming through, and we have hundreds and hundreds, and we can get even better iterations as we kept going. And as we saw, our factor of safeties were actually a little bit higher than they could be. We don't need them that high, so we're expecting the following team, the following year, for them to bring down the factor of safety and the weight a little bit more to be more efficient and produce more performance out of the vehicle. And also cost to benefit ratio. We went with aluminum. We wish we could have gone with carbon fiber, but it's just too high in cost, and again, we have the budget issue. Conclusion, everything was redesigned. Our biggest redesigns was the double wishbone assembly and also our tripod assembly, which gave us more power and lowered our weight. And again, we are in the competition, and we want to get the lowest score of 20 out of 25, but we're always reaching for the top, so we want that 25. We thank everybody. We thank FSAE for their funds and everybody else that funded us. We thank Trevante for being our advisor, Professor Tosunoglu, and Mr. Zigaregli for manufacturing, and all the FSAE teams that helped us out throughout the way. And we now open the floor for any questions.
Also, we would like to invite you to come to the shop. We couldn't bring the car in because it's too big, and to disassemble it would be a big process, but we can go ahead to the student machine shop, and you can see the completed fully product, and we can go over if you have any additional questions.
The main part why we couldn't bring it in is because the brake fluids and stuff, it's quote-unquote regulation illegal. So if you want to see it, we can take you to the shop.
The car doesn't fit through our elevator. Yeah, okay. Your car weighs like my car.
I think you brought the pipe with this meeting.
Well, we hope the video kind of showed,
That was great.
Great. Any questions?
Any questions?
So I have some observations. First thing, carbon fiber is not always the solution to everything.
No, we were just going for the lighter material. That's the only reason why I said that, for just cost versus benefit ratio.
But it might not serve the purpose that you're looking to get out of
Right.
the material.
Right.
So just remember, it's not always, everyone says carbon fiber is this golden egg, but it's not always the best.
No carbon fiber can't take maybe as many forces as steel and other materials can.
And heat.
And heat. Yes.
There's certain components that we tried to maybe, or we were thinking of putting as carbon fiber. For example, some of the tubing, maybe the control arms, some of the push rods, the pull rods, which other teams do run as carbon fiber. But unfortunately, our budget is not as high as theirs.
And it's usually has to be laid up. It's not automated. So the second one is watch out for singularities in your analysis. I've seen every presentation just put up your ANSYS plots, but don't just run the analysis. Understand, does it make sense? I've seen a lot of times where you have elements that might not be telling you the right story, or might be skewing your results. So always, after you run the analysis, use your engineering judgment to understand if the results that the computer is pushing out are actually what would make sense for the results.
Okay. Thank you.
Any other questions?
Get away that quick. You talked earlier about reducing weight and also, in fact, increasing power transmission. But by how much?
Oh, yeah.
I mean, you have to be very careful when you're doing reports and your proposals, etc. It's not sufficient to say you reduce weight and you increase power. You have to say by how much. So how much?
It was I don't think we have it here, but in fact, that was the component from the entire suspension that had the biggest difference in weight. So we do have it in the report, but as you say, we should have as well listed here.
Do you remember what it is?
If I could chime in, I'm president of FSAE. So the biggest part, or one of the biggest weight components on the car, by part, is the CV axles. And the fact of the matter that the CV axles, the input spline shaft, which drives the rear wheels, it's a solid chunk of steel. So it weighs probably about 4 or 5 pounds. Just the part that we're talking about that goes into a normal car that would be the drive. It has splines on it. By having your integrated hubs that Yussimil and the suspension team designed, it's cut down on at least 10 pounds of weight because we were able to eliminate those end pieces. And also,
I get that. You
Yes.
need to say
No, you
what?
just want
Yeah.
the
Yeah,
percentage.
yeah.
If you're gonna say
You know,
percentage, not really.
You're doing it from based on some sort of
Yeah.
baseline, maybe from last
Yeah,
year or
we got
whatever
last
it is.
year's results and then
So-
compare it to weight and
so it's a-
speed now.
5% reduction
Right.
by weight.
Right.
If I could, I would like, going to my computer, have it there, but I understand, yeah, that we should have that for the year. It's in the report.
I would like to say we lost at least 20 pounds.
I do understand why you,
All the comparisons are from the previous team, and then now with all of the analysis that we've done and all the calculations, we are passing that down to our future group.
Yeah, we want them to take over all our redesign stuff and make them better, as we were saying. And then, of course, talk about percentage.